So far in our discussions, we've been using mostly feedback control. And feedback control has proven to be a very useful tool that allows us to maintain some kind of controlled variable, such as a temperature or a concentration in a reactor, close to a set point value that we care about. And while that is good, one of the problems we have with our feedback controllers has been that we realize error in our process. Our controlled variable will be different from its set point for a certain amount of time, or in the case of P-only controllers, for instance, we may have offset. And so if we wanted to completely reject disturbances in our system, we will turn to feed-forward control. And there are some key things to note before we start to dive into the control block diagrams involved. And the first thing is we must be able to map how a disturbance interacts with an output. And the output in this case will be our controlled variable of interest. And so to give an example, to add some physical intuition to this, let's consider if we had some kind of large metal cylinder containing water, and we had wind speed outside if it was exposed, and we wanted to be able to predict based on the wind speed the temperature or the heat, how much heat we would need to add to maintain it about a certain temperature. And so we must be able to create a transfer function block called GD. And so this GD block is very difficult to actually create. And in addition to that, there might be other disturbances that we don't really know about. So it gets very tricky. But if you have the ability to understand fundamentally how some of your disturbances are going to interact with your process and create transfer function blocks like GD, it is very useful. Number two, we never use feed forward exclusively. So we use it in conjunction with feedback control. And the reason for this is because even if in a perfect world we knew every single disturbance that might interact with our system, that isn't to say that our process model is perfect. There might be inaccuracies in our model. Our system might evolve with time if we get buildup of whatever thing in our reactor and the volume changes slightly. So we need to have feedback in all of our reactors, or our control block diagrams. And then finally, we must be able to react quickly enough to the disturbance for our feed-forward control to even matter. If we could perfectly model how the wind speed's going to change, but if the time scales that our heaters work at are too slow, the whole concept of feed-forward is kind of pointless. It might add a little bit to it, but we're not realizing the full efficacy of feed-forward control. And so with these things in mind, now let's go into what a control block diagram would actually look like. And so, as always, we'll have some kind of demanded set point, such as a temperature or a composition, and we will be considering, or we will first be deriving the air that is present. We're going to be passing that air into a feedback controller GC, and from this feedback controller GC, we will have the addition of the output from our feed-forward controller. And from the feed-forward controller, the input to that will be the transmitted disturbance. So if we had to measure the wind speed, this would be the airspeed meter, whatever you call it. And finally, we would have the disturbance itself, as well as the transfer function block GD, which is how the disturbance will interact with our system output. And we'll put that there. And then, so now, down here, what we'll have is the valve dynamics. If we were having to adjust some kind of flow rate, how the valve is has the transfer function, and then we'll have our process itself here, and we'll add these two terms together to arrive at our actual output y, and then we may have measurement dynamics that we would need to account for here that we take with our GM block, and this is the main takeaway for feed-forward control. And so the million-dollar question to ask here is, what do we set GFF to be, our feed-forward controller transfer function? And so GFF, and you can look this up in a textbook and use control block algebra to verify, is equivalent to minus GD, the transfer function of our disturbance variable, divided by GP, the process dynamics, times GT times GV. And so if you are able to fully understand what GD is, this was the most tricky one to figure out, and you'll be given this on a test, but in real world, figuring out what GD is the challenge. And you know these other parameters, you will be able to design a feed forward controller. And so to test if your feed forward controller is working, if you analyze the time response of your system, and we'll have some kind of step time. So if we went into Simulink and we had our disturbance variable D here suddenly go up to a certain value, like if we had our wind speed suddenly increase to 10 miles per hour in the southwest direction, it would occur at 1 second in our model. That would be our step time TS. What we would find if we could respond fast enough to it and we had a good enough model is that nothing would happen to our set point, so our set point temperature, for instance. And so this is the ideal. And so this is what we want with feed forward control, and we do the best we can to get there. And this kind of wraps up the why we care about feed forward control and the math behind it, as well as the control block diagrams. Let me know if you guys have any questions, and thanks for watching.